Thank you very much for the invitation. I wish I could be there, and I'm sorry to subject you to a Zoom talk, but in-person teaching is needed. So I'm going to talk about some recent work and ongoing work with Bruno De Luca, which actually benefited largely from discussions with Mike and with a bunch of people who helped to stimulate this direction for us. And I'll be able to give a little bit of an update as to what we're doing with it these days. The paper on this topic appeared a couple months ago, and this concerns a method kind of spinning off lessons we learned in early universe cosmology for the problem of optimization and now potentially sampling, which is a problem that appears all over science. So we're having a lot of fun with that connection. And in this area, it's one of the big trade-offs is exploration versus exploitation. So do you go along a trajectory that seems to be doing well, or do you try other ones that might do even better? And this is a standard challenge in the field, but there's at least one existence proof that it can be done well. And sorry, I'm trying to move my screen. And that is Mike. Now, admittedly, Mike is a human neural network, but still, it's a wonderful existence proof of how successful it can be to have a breathtaking array of really deep interests and to contribute across the board. So we all know that the field really, it is where it is today, owing a great deal to Mike's work in all these various areas, starting from matrix models, the nuts and bolts of brains and gauge theories, the landscape and geometry and some of its statistics, and machine learning and its connection to mathematics. And personally, my work goes a lot to Mike. Just listing a few examples here. He has famous estimates with Frederick Deneff on the tunability of Calabi-Yau flux vacua of the KKLT type, which led them to an interesting formula for essentially the prediction for the horizon entropy, which is of order flux numbers to a Betti number, not a matrix model type thing, which matches nicely the brain degrees of freedom in the system. My own main interest in that subject has to do with the more general case of curved internal spaces, and there also Mike's work is extremely important. Quite recently, he wrote what I consider to be one of the most important papers in the landscape. It's not maybe the most well-known, although it should be, which contains an elegant and very model-independent formula for the four-dimensional effective potential, which I'll touch on later. He also was one of the early people spelling out the phenomenon of monodromy in string theory, which has interesting implications for inflation in string theory. So this is just a short list of the many contributions. And again, an amazing existence proof of the possibility of the success of both exploring and exploiting. So lately with Mike, we've had many discussions on AI and its applications. And so it's in that field that I'll continue to explain this recent and ongoing work. So for those who maybe don't think about this all the time, for many problems, one needs to minimize what's called an objective function or a loss function. Let's call it V. And one needs to, in some way, descend such a landscape, which generally is quite complicated, non-convex, high-dimensional. This arises in data science and data analyses of all sorts, including machine learning problems. Another application, which is also, I think, dear to Mike's heart, is using it to solve PDEs, for example, considering neural networks as ansatzes for solutions to PDEs. And in that case, at least the most simple-minded way to set it up is to take this loss function that one is trying to descend to the bottom of to be just the sum of the squares of the PDEs, and including the boundary conditions. In this case, in particular, one really wants the global minimum at 0. And again, it's something that appears all over science, as does the problem of sampling from a distribution. And so we'll consider both optimization, mainly optimization, and also sampling, which we're generalizing into these days. So, well, this is being a very common problem. there are many methods, and often they work very well. And so we're new to this, and we are suitably humble about our results so far experimentally. But as you'll see, we find a very distinct mechanism that has certain advantages, and we're finding it very exciting to push it forward. So there are many types of optimization schemes, some that use certain properties of this landscape, like it having a computable gradient or even higher order derivatives. And in that context, gradient descent is kind of the traditional standard method. And in machine learning, that and various variants of it are basically the methodology. And it can work very well with a number of sort of tweaks that people developed over the years involving the discrete learning rate, the extent of the discreteness in the time evolution, varying with time itself and such things. But it's not perfect, and sometimes it gets stuck or doesn't, and there's no reason for it to sample all the desired solutions. So what we're going to talk about is a method that is quite distinct from that. So whereas gradient descent is like frictional evolution on a lost landscape in physics language, we'll work with a mechanism that was inspired by certain early universe inflation models, but abstracted from that, where there's no friction at all. And yet it will fly around and stop or slow down where we want it to, near the bottom of this potential V, up to so sometimes the potential, the goal is to get to V equals 0. Other times there's a constant shift relative to that, and we'll talk about both cases. But just as a preview, the idea here will be to take a relativistic speed limit squared, which is a function of the loss, say just V itself, without any friction at all. And so it flies around unimpeded until it gets where you want it to slow down, and there is where it slows and stops, but not before. The nice thing about this from a physics language is that it's consistent with energy conservation, unlike frictional evolution where you're contracting the phase space. Instead here, we don't need any friction at all, so we can preserve energy conservation in the sense of the physical analog of a particle flying around on this potential energy. The closest analog we find in the literature does need friction, which is, it's called relativistic gradient descent, where it includes the relativistic aspect, but does not include the aspect where we take the speed limit squared to depend on the loss, which is the key element here. Okay, so for PDE solving, let me just schematically explain at least the simple-minded way to do that. So that goes back to many papers, maybe this one in '97. Douglas Mike has done great work on this in looking for Calabi-Yau metrics, for example, and whatever else. So again, the basic idea is to take a neural network, which is a nonlinear function built from some inputs and iteratively applying a weight matrix plus a bias, then process through some nonlinear function point by point to build up a certain type of nonlinear function, which whose outputs we'll call y and inputs to this we'll call x. We'll call the matrix of so-called weights relating the different layers w and the biases b collectively as parameters theta. Okay, so for the problem of PDE solving, this is just some particular form of an ansatz where we then want to descend a landscape which consists of the sum of the squares of the PDEs and the boundary conditions. Incidentally, people have played with beyond classical fields or PDEs, thinking about formulating quantum field theory in this language in various ways. But this is anyway the schematic of this approach. In machine learning, there are various variants of machine learning. In the supervised case, the loss function, when is descending, can be as simple as sum of squares of output of the neural network minus the true answer summed over the data x. We're also playing now with quantum chemistry as an optimization problem, where essentially the loss is the expectation value of the Hamiltonian in some standard set of trial wave functions. So these are just 3 examples of the kind of problem that I was mentioning. Okay, so I said we're going to get there from ideas in early universe inflation. So let me just remind you of that and explain how that enters. So early universe inflation requires, one way or another, a nearly constant potential energy. Let's call it V of phi. In that context, this nearly constant potential energy is the source for inflationary, for accelerated expansion of the universe. And when it's nearly constant, you get that acceleration. One way to do that is have Hubble friction dominate. So that's the traditional slow roll inflation, where you have certain flatness conditions on the potential, which can be natural. And again, Hubble friction dominates. There's a whole nother class, which was illustrated originally by what's called DBI inflation, where instead the potential could be quite steep, but interactions conspire to slow the field down and keep the potential energy constant. And in this case, the speed limit, it's a Born-Infeld type action with a squared speed limit depending on the field phi. So one version of that is given by this action here, where you see inside the square root, the field velocity phi dot squared with some coupling parameter lambda depends on the field phi. And in this context, it must slow down as phi goes to 0, no matter what the potential energy is doing. So, in that context being so fully nonlinear, it's also predictive of non-Gaussianity, so to speak. So some imprints of the interactions, and there's a particular form of that is undergoing empirical testing, sort of halfway through the parameter space in some measure. And there's ongoing work to try and get all the way through the parameter space using large-scale structure data, which is in itself a wonderful challenge in the field these days. The thing we're going to extract from this is that, which we realized the community in early universe cosmology understood very well back when this was discovered, which is this has very distinct behavior and hence, as I just said, different predictions from slow roll. It's kind of in a different category. And for optimization, the analog of slow roll would be gradient descent, where friction dominates. Now, what we're going to extract from DBI or BI is actually the non-gravitational version of this, so that we can have the property of energy conservation that I highlighted in words earlier. So for that, we take the action, let's say in the case where we're aiming to get to V equals 0, we take the action of this form. Now using the notation that the parameter space theta that we're interested in exploring, the parameter space is denoted by theta, as I said earlier. And in a continuum limit, this would be the action. Or in terms of the canonical variables, the conjugate momentum, we can write it as usual that way. The Hamiltonian gives a constant conserved energy expressed either in terms of theta dot and V, or pi, the conjugate momentum and V. And okay, so because of the energy conservation, it's simply impossible for this, let's start in the continuum limit, to stop at a local minimum, generically. If it's stopped, that would require either V equals 0, basically V equals 0 here, right? Given a generic constant energy. So, unlike gradient descent or some frictional method where you're contracting the phase space, that's just an impossibility. One thing that can happen though is it can get stuck in a long-lived orbit, and we have methods to kick it out of those orbits, and that I'll mention shortly. It also can't overshoot V equals 0, at least in the continuum. It has other properties that that we can derive in a little bit more detail. I'll mention later that it works faster than gradient descent in shallow valleys of the landscape, which is something of interest, at least in some of these contexts. Okay, but for now, let's just notice it's as such, it's very different behavior from gradient descent. Whatever else is true, it's gonna have different advantages and different disadvantages. Okay, so because of energy conservation, we can work with the conserved phase space volume, and looking at that, implementing the energy conservation via the delta function here, and integrating over the momenta, we obtain an expression for the volume in parameter space theta that we can already see from this formula strongly favors the region near zero loss. So that'll play in our discussion of how this optimizer behaves and what kind of advantages it has. At this point, let me again just note that we are able to use the energy conservation to gain some mileage from the calculation, the conservation of the phase space volume, which will favor the region of interest. Okay, so, well, this is somewhat nostalgic, at least for me, to work with this model, but it's really just one of many, many possibilities. In fact, the simplest in this theme would be, say, taking the mass to go inversely with the loss, like take a normal two derivative action and take the mass to go inversely with the loss. It has the same properties. It has energy conservation, and so it needs no friction, and it can, but yet it stops as the loss goes to zero. In this case, because the mass blows up. So we have, at least among ourselves, named this entire class of optimization algorithms energy conserving descent. Okay, so let me take the rest of this part of the talk to spell out a little bit, much more about what we've learned about this, both analytically and experimentally, meaning through numerical calculations. Okay, so this is, a physical model in some complicated landscape, and you might expect the dynamics kind of generically to be chaotic, at least at high enough energies. But, one can find situations where instead it finds long-lived orbits. But as this is now engineering, we're not modeling nature with this particular model. We're liberated to add elements to the algorithm to encourage it to behave chaotically, so that it can realize after a small mixing time the predictions of landing in these favored regions of the phase space volume. Okay, so here's an example. So here's some PDE with a somewhat complicated form that we set up because we know the solution and we can check the success of the algorithm. Okay, so in this case, here's an example of some run where we see that it does get stuck. It doesn't make progress down the landscape after a while. In situations like this, one can lay out that it is finding some orbit, but then we add some feature of the kind that I'm alluding to here, and it kicks it out of that and it gets unstuck. Okay, so just to pursue that analogy a little bit more physically before saying how we really do this, this BI action is a lot like redshifted gravitational physics. So test particles, say in a black hole or a galaxy, and there, the role of chaotic dynamics is very familiar. Here is a random example from studies of galactic dynamics where you find both chaotic orbits and periodic orbits on a slice, Poincare slice, that's laid out here according to some numerics. And for us, we just want to set it up so that it has that aspect and explores more. So inspired by mathematical billiards, where people have proved short mixing times, exponential mixing, and other properties in cases where they could rigorously do so, including cases where they could scale it up in dimensions. Inspired by that, we add a kind of bounce, like a billiard ball bounce, in order to encourage the mixing property. And let me just say what the basic intuition of this is. So this is related to the idea of sensitive dependence on initial conditions. And so if you think about a bounce off a billiard ball, as you approach the billiard ball with, say, parallel trajectories, you bounce off with much more deviant trajectories. And so such a bounce realizes the idea of sensitive dependence on initial conditions and causes the trajectories to fly away from each other in a kind of discrete analog of the way that negative curvature does so. And all that goes in the direction of encouraging the mixing property, which is a stronger property than just ergodicity, where after some time, which we hope to be relatively short in the computation, if, say, we start with a droplet of trajectories, then after that mixing time, one has a prediction that the probability of finding the particle in some region of phase space is proportional to that phase space volume. And okay, given this assumption of mixing encouraged by these bounces, we have that prediction as a result, again, of the energy conservation. So not something one could have predicted for gradient descent. Okay, so there's a lot that goes into actually implementing this. It's a discrete update rule that starts by just discretizing the continuum theory in a first order formalism with the position theta and momentum pi, using the energy conservation to express things in terms of E and V here. There's a number of options, so you can specify the energy starting with some momentum or starting just at zero momentum high up on the potential landscape. Numerically, if you start building up numerical errors, energy conservation can fail, but this, again, being engineering, we're liberated to just enforce it throughout by rescaling the memento. So we implement that. It's not always essential, but we have that. This business of the bounces can take two forms, either as in the plot I showed, if they're just conditionally, if there's not enough progress as defined however you wish, then we introduce bounces, or you can just have bounces initially. And so that helps randomize the initial, essentially the initial conditions. So both conditional and definite bounces of the billiard sort that I mentioned. Okay, so this is basically a summary of the algorithm. There's something else that we're improving it with, which is, so I discussed this as though we know that the goal is V equals 0. And kind of nominally that's true with, say, machine learning with a MSE loss, but even there, the data can force you away from that. And in many cases, you might just not know. You might be given an objective function that you want to descend, but you don't know the value of the global minimum if that's your goal. Okay, so we don't have any so-called hyperparameters defining the strength of friction, which is just absent for us, but we do have this hyperparameter, which is a shift of the overall goal. So if we have some objective F, we can shift it by just, for lack of a better word, some constant delta V. So one can think of this as a hyperparameter to tune, but actually there's a way to kind of self-tune it. And so in fact, if you overestimate this and you discretely jump past V equals 0, now the new version of this code just conditionally on that shifts down delta V, so the new goal is below. And if you keep finding that you can jump over that line, you just keep going down. And so it is working out to actually self-tune this particular hyperparameter. We're studying this particularly in quantum chemistry experiments these days. Okay, so here was our measure formula. One thing we can do with it is look at what it prefers in terms of different types of local minimum basins where we have a Taylor expansion to a quadratic approximation to the local minimum. And if we put that in and ask for the measure in a region with a certain value of V at the minimum and a certain essentially Hessian or Hessian mass matrix around that, and simply plug that into the general formula. Here's what comes out. I mean, it's some hypergeometric function, sort of integrated up to where we reach order 1 values of n times the theta deviation. And so the upshot of that is that there is a preference for, as we saw initially from the formula, for V going to 0, either the original loss going to 0 or loss minus delta V going to 0 logarithmically. And there's also a power law dependence on the eigenvalues of mass matrix here. And so it also prefers shallower minima, which is apparently a thing in machine learning that may be an advantage. So I'll show you 2 things. One is to check this in sort of small scale experiments. In fact, our experiments will illustrate all these features that I'm talking about, but I should also say at the same time, they are small scale. And one of the things we're doing now is to scale them up, trying to assemble resources to be able to do that. So I'll show you that. And also show you how nowadays we're looking at applying the same type of formula, descending from the energy conservation, to give us a method for sampling as well as opposed to optimization. Okay, so here's the small scale, but rather clear example of the measure formula working out. So 2 different basins, slightly different in terms of their minimum value and their mass matrix. With the bouncing, the trajectories go all over, and the experiment lines up with the theoretical prediction for the relative importance of the 2 distinct minima. Okay, so now let me come to this business of sampling. So this also comes up all the time in data analyses and trying to compute integrals and so on, where you want to sample from the important part of some function. If we express that function as the exponential of minus some f of theta, then we can simply choose our model among these energy conserving descent type optimizers, or in this case samplers, in order that the resulting measure formula line up with the desired sampling function. So let me illustrate that with this other version of ECD, where we take the mass to depend on f, the objective function, or here the sampling thing being its exponential. So there's going to be energy conservation of that. And there, if we just apply the energy conservation to the phase-space measure, then we can determine that in order that the result be exponential minus f, our desired distribution, then the model we should pick has a certain form. So this g of f should be, in this case, it turns out e to the 2f over n, where n is the dimension of the parameter space. Okay, so now at small scales, a bimodal distribution, it does sample that well as predicted here, given that we set up the model in this way. So the plan is to, again, this is a subject that's got a very beautiful history, and we will now study how it compares to the standard methods, including Hamiltonian Monte Carlo, which is sort of similar, but actually quite different. There you have a separable Hamiltonian, and you sample from the quadratic part of it in a different way. So we're working on this, I should say, with Uros Seljac, who's a expert in that domain, including applications to cosmology. Okay, so now let me come back to the optimization examples and just show you a few examples where it worked out. So more of the PDE solving using examples that we humans know the answer to. And we indeed find that this algorithm does find the solution. This is the solutions plural. So in this case, there's two solutions and it finds both of them, this one and this one in this particular example. So again, we predict that it should find multiple solutions and it is doing that. So we already went over this measure formula and how it prefers not just small v, but also flatter minima. And in machine learning, there's some lore that might generalize better and that shallow directions arise a lot in that sort of landscape. If you look just a slightly more at the details of the evolution in such regions, also one finds that in BI, the speed limit dominated motion is faster parametrically as m, the mass goes to 0 in a shallow region compared to gradient friction dominated gradient descent and even with momentum. So, well, we saw that observationally. In fact, we were a little bit slow. We saw it observationally first and then figured out why this was happening. So here's a synthetic loss function where you see that happening with gradient descending much slower. Okay, so here's our table of distinctions. And one thing that might be on people's minds, if you've thought about these things, is whether we've focused too much on the kind of pristine situation without noise, where we've input all the input at once. But it does actually persist with the kind of noise you get by taking batches of the data, smaller batches of the data. Okay, so but first let me just show a few more examples. So here's a very non-convex loss function, and doing a kind of optimization, optimization procedure for the hyperparameters of the various optimizers. We find an advantage for bouncing BI. So here's a plot of the loss, a plot of the function, and you see the kind of trajectories that it carries out. And there's some fine structure in this sort of thing where, so just to be clear for those who don't think about these things all the time, by hyperparameters, we mean things like the learning rate, how the size of this discrete step delta t that I wrote, and in the case of gradient descent, how strong the friction is compared to the momentum. And in BI, things like how many of these bounces do we introduce and such things. Okay. So, well, here's another example, highly non-convex, similar results, also small scale, but, you know, dimension 5, dimension 400. So as at least an important detail for those who follow these things, in reality, one usually can't input all of the data at once. So one has to do it in so-called mini batches. And in this context of the physical models that we're talking about, descending the landscape, what that corresponds to is essentially a time-dependent potential, where you input some of the data and then you switch to other data. And so the potential kind of jumps around in time. But again, being engineers for this purpose, we can just force it to the original energy no matter what. And as such, it just retains the same kind of theorems, trivial theorems that we have regarding its evolution. One thing that's quite interesting in these things is to incorporate the noise and study more about it. So already in gradient descent, this is a thing. So people try to understand the version of essentially Brownian motion that one gets in that context. And one needs to be very careful about continuum limits. And there's a nice paper by Yaida, for example, that just keeps it all discrete and computes fluctuation dissipation relations in the discrete setting that is relevant. So, you know, traditional Brownian motion, of course, has this behavior of v squared t. But for BI, it's quite different. The speed limit, is an absolute limit on the motion. And so in that sense, there's less Brownian exploration for this reason. So this will be something interesting to understand the implications of. But it's kind of both a benefit and a complication of stochastic gradient descent. So this is a comparison to BI where it's a little bit more controlled for better or worse. Okay, so there's some very standard, again, low scale benchmarks, and BI can handle those, and those do have this noise property. This is really just a test of basic competence. It's not, we're not at the resource scale where we're finding any way to distinguish. It's sort of like a very easy standardized test. But it does illustrate that it works with noise, that it doesn't overfit. And that's because although it only strictly stops at v equals 0, so the danger here of overfitting is in machine learning that it exactly models the data, including the noise in the data, and doesn't really generalize to unseen examples. But it doesn't literally only, it slows down before getting to v equals 0 is the explanation for why even here it does indeed generalize. So this illustrates that. And again, as I was saying earlier, our plan is to, if we can at least get resources and so on, is to scale up to more state-of-the-art problems to see how it works there. One of the interesting aspects of this is the question of so-called feature learning. So let me come back to the picture of the neural net, and this is going to be, again, a very simple-minded description of this issue. But okay, the way it works, as we discussed quickly earlier, is that you have some inputs x, some output y, which is a processed, nonlinear function processed through the various layers of the neural network. The output layer is linear. The other ones are nonlinear. And okay, so from this point of view, in order to not just be doing essentially linear regression, you need all the layers to update, at least not just the output layer to update. And people realized, as reviewed in this nice book by these authors, that if you take kind of what's called a standard initialization of everything and as a function of the width of the neural network, that as you go to large width, you get a well-defined large n, large width limit. But where it reverts to linear regression, the Gaussian process. And so that enables perturbative techniques to study feature learning, which then depend on the ratio of depth to width being, once that's finite, which of course it is in reality, that's where you see the feature learning. And so you can do a kind of perturbative expansion around that. On the other hand, for practical reasons, you might not want to take that large width limit. You might want to, if you're scaling up to large width at all, instead you might want to define another stable large width limit that actually preserves feature learning. And there's interesting work in the community by Yang and Hu doing that. And all these studies, in this problem, all the various aspects are related to each other in nonlinear ways. The choice of neural net, the data set, and the optimizer. So in particular, all these things are dependent on the optimizer. So we want to understand how it works for this BBI or ECD. And there's one simple comment one can make on that question, which is that the diverging trajectories that we introduce with these bounces, if they're not already present, is enough to kind of kick it in direction to learn in the hidden directions, even if it wasn't already doing so. Just at that level, it does seem inevitable that only, if only because of the bounces, it will do the more interesting kind of learning, the feature learning. Whoops. Okay. So that's one direction in progress. In terms of applications, we're looking at a very fun set of problems in quantum chemistry where we implement this for giant molecules that are interesting to try and find their stable or metastable configurations with a expert in that field that we met in the Stanford Data Science group. And also sampling, as I mentioned earlier, this was also brought to our attention, I should say, by Urush and also Miranda Chang. And we're hopeful that for the reasons I mentioned earlier, that this could be a successful application of the energy conservation formulas. With what time remains, let me apply it to certain PDEs that are of interest. Back in the subject of string compactifications. So this is an area that of interest that many of us share, that we've enjoyed many interesting discussions with Mike on over the years. And there's a lot to say about this. Let me start somewhat general and then just flash again a sort of small scale example of this in the context of interest here. So this, aside from the generalities, this will be work with Bruno and also Gonzalo Charoba. Gonzalo can be considered another of Mike's many successes as a former student of Mike's who's gone on to his own brilliant career. So this application concerns particular PDEs that arise in string theory where we have extra dimensions and transitions among dimensions, topologies, flux quanta, and such things. So it's a very complicated problem. But in certain regions of this vast landscape, we can study it in depth. And the point being, one gets mechanisms for the accelerated expansion of the universe, the early and late universe in string theory, leading to model-dependent tests in a UV sensitive setting, also giving us some ideas for the problem of upgrading so-called holographic duality to the case of interest, which is the accelerated expansion in the universe, the de Sitter, as opposed to the anti-de Sitter case. And related to the current talk, it gives some interesting targets and, as we've seen, some interesting methods for numerics and machine learning. Okay, so here's this formula of Mike's that I am probably the biggest fan of, which is his formula for the effective potential descending from a higher dimensional theory of any sort. I've written the version of this that applies in perturbative string theory, and we'll use a simpler version of it shortly. But what this does is it defines the four-dimensional effective potential of the fields that descend from the extra dimensions of string theory in a way that implements the necessary gauge constraints of general relativity by first imposing the constraint, the internal components of the constraints to do with the variation with respect to the warp factor u, or e to the 2a. And having imposed that, to plug it into the dimensionally reduced theory to produce a well-defined formula for the effective potential that has solved that constraint. When you set that up, you learn interesting physics like that this expression is like a Schrodinger problem, and the way it works is, in terms of the signs, is that negative contributions actually produce a potential barrier in this formula, so that the warp factor, like a wave function, screens those regions, so it dies in those regions. And this, in fact, explains why compactifications are not massively unstable due to the famous negative conformal mode contribution from the derivatives of the conformal factor B here. So it's a very nice general formula. In terms of what enters into it, there are various stress energy sources that come from the leading terms in the potential energy, fluxes, axions, important negative contributions due to the so-called Dine-Seiberg problem. The simplest way it works in directions like the inverse volume is to have a kind of three-term structure with a negative term that's crucial. And there it comes from things like exotic orientifold planes, objects in string theory, quantum effects, either perturbative or non-perturbative. And the way the warp factor enters introduces contributions from both internal and warp factor variation curvature contributions. So most of the contributions are positive. They're negative contributions that matter. This formula can be applied either for flat or curved extra dimensions. And again, teaches us a lot of physics along the way. Okay. Now, of course, this is an old subject. There are lots of examples, much reviews, including times by Mike and others. Here's a laundry list of examples. And the one that we'll think about here is this probably newest one that involves compactification of a certain limit of string or M theory, the 11-dimensional supergravity limit on a hyperbolic space, motivated by the mathematical properties that those have. The metric is known, it gives positive potential energy. It starts with a rigidity property with a very strong positive Hessian in every direction. Once we include the warp factor lifting the conformal mode. And among internal spaces, it's much more, it's very generic to have curvature. So another aspect of these examples is that they provide a direct uplift of an ADS-CFT system. So there's an ADS-CFT system involving certain types of branes, M2 branes, corresponding to M theory compactification on a sphere. And what this is uplifting that to M theory compactification on a hyperbolic space. Okay, so this is a long story. I think maybe other people will be talking about other examples, like maybe Liam will talk about this case. There's a important understanding of how these things work and how they're controlled and so on. Okay, so here we do our sort of pandemic paper with Bruno and Gonzalo was this example that I just described in words. I'm looking at my watch to make sure I'm on time, and if I'm going over or missing that, just let me know. So this example is based on the internal negatively curved spaces, which have the Mostow and also geometric rigidity property that I just summarized, and combining that with Mike's warping gives us a strong positive contributions to the Hessian around a volume stabilization mechanism, which works very simply with a positive contribution from the negative curvature, Casimir energy playing this negative role that I mentioned, and fluxes. The role of the warp factor that Mike explained is crucial here as well in the way that we find a parametric tuning available to, in fact, tune down the curvature contribution using the contribution from the varying warp factor. So this case has a certain simplification in the effective potential formula. There's no so-called string dilaton here. And so this is just the formula as it applies to these new models. We work with very explicit hyperbolic spaces introduced by a group called Italiano et al. That came out recently. And this is just a cartoon of how it works. One of the things that Mike introduced along with Renata Kalash is a key member of the set of PDEs in this problem, which is this one that relates the net curvature to the various sources. Here, the magnitude of the Casimir energy and the fluxes, and you see the signs that they take here, which is important. And so we find that using that, we can parametrically tune this ratio to be small. So if it's too large, we understand how to take covers or change the so-called cusps of these hyperbolic manifolds explicitly in a way to decrease this A. And if it's too small, we can easily increase the very finely tunable contribution from the fluxes by tuning the flux quantum number. So, there's a long paper and longer online talks on this subject, but this is giving you sort of an idea, and I'm highlighting it because of its, well, we're interested in it, but also its relation to Mike's beautiful formula. So we basically do this analytically with these control factors that I was just summarizing. However, it is interesting to ask about the details of the internal PDEs, both just in this region of analytic control ability, but also beyond that. So what happens to this theory, this effective potential, if we go to regimes which are more difficult for humans to solve. So just as a teaser for that, we did an example of an sort of lower dimensional space solving analogous PDEs using the kind of method, the neural net ansatz that I mentioned earlier. And one finds that it works out. One can do that, and we'd like to extend it to these higher dimensional examples. I want to stress that this is a well-posed problem. We know the initial metric. It's a little bit easier in that regard than the Calabi-Yau case. We know the fiducial metric. That's not the mystery, but what, of course, in the Calabi-Yau case, there's a theorem that says it exists. But anyway, here we know it. The projection that we do to get the finite volume space is known. It also determines the Casimir energy. The flux solution is known. And we have, our human idea about where we might start this exploration numerically. Another interesting thing is to just study Mike's formula for V effective or its various functional derivatives, which give slow roll parameters as loss functions to just explore and hopefully exploit. Okay, so here's a summary. I think I am coming to the end of the time. This was the basic idea. We have a prediction from the measure on phase space for the results of this optimization and sampling procedure. We've illustrated it, but only at low scale. And so we're applying it more widely, so exploring more, and also to exploit, trying to look at more and more higher dimensional problems. And so on. Okay, so let me end with the most important thing, which is to say happy birthday again to Mike. I'm amazed at all that you've done, and I thoroughly enjoy every discussion I have with you. It's always a pleasure. I do have one request, which might interest you at this point, which is, among all these things that you contribute to, could you perhaps add longevity research just to help us all out a little bit? I'm sure you could succeed at that as with everything else. Okay, just kidding, but happy birthday, Mike. Let me stop there.
It was great talking to
you. Thank you, Mike. I'd love to discuss these things more, as we often say we will.
I had a minor technical question. What in this method of solving the PDEs by basically taking the sum of the squares of the differential of the PDE itself at the different points where you're evaluating it and just going downhill by some method or other, what does mini batching amount to here? Just imposing the condition at some subset of all the points that you want to impose it, and then just keep hopping the different subsets?
Yeah, it's a similar thing. It's indeed, how many points do you sample? Of course, it's some finite number. And you eventually you would want to prove convergence by sampling more and more points and showing that it does converge, right? But as in machine learning, you can sample different points for different steps. So it's exactly, it's what you said.
Oh, good. I'm proud of myself.
No, definitely, it's basic.
Okay, nobody else has a question. And the other one is, okay, I thought I know very little about this whole area. I'm kind of very interested by it, but I thought somehow the lore was, oh hell, you don't have to worry about non-convexity. Stochastic gradient descent hops you over all of these little traps and gets you to the global solution. And so this DBI method, so to say, has a natural way of hopping over local as opposed to global minima. That sounds very cool. I mean, how much do you gain? Are you losing something when you're implementing this? Is you making your life harder? I guess my question is, do you have a sense now of what's the overall potential gain? Are we going to solve hard problems faster, or are there new problems we couldn't solve in the, so to say, garden variety optimization methodology?
Yeah, I mean, the hope is to do both, but it remains to be seen at large scale. So it's a great question. So what I did do in the talk is show you some places where it's certainly different, and in those ways it is advantageous. As you also say, after all, there's this explosion in work on machine learning and AI, and as SGD and its kind of descendants, there's one called Adam, which is more kind of adaptive version. They work, right? But it does lead you to wonder, could it be done better or faster? And one way to say that is, well, people do these giant models and they train those, and then they realize, I mean, sometimes there's some problem where once you have that result, you can compress it and do some task with the compressed version. And could you have gotten there more directly? So there's a lot of elements to your question, including what kind of loss landscapes is it that matter in various problems. And I mean, the short answer is this is too soon to tell, exactly what the best application of this will be in comparison to gradient descent, but it's so different. And well, let me also say a couple more things. So, well, okay, in quantum chemistry, we're actually working on some problems where the other methods hadn't worked, and we're getting somewhat lower on the loss landscape for some such problems. So there should be some news on your question, coming up. But yeah, let me just back away to bigger picture. There's this famous, no free lunch theorem, right? That if you know nothing about the loss landscape at all, I mean, including differentiability or anything, there's no way for any one optimizer to always be better, right? And it's almost it almost sounds vacuous, but it's a proper theorem. And so what that says is, there are problems where different optimizers will have their advantages and others where they'll have their disadvantages. And so your question is exactly where we're headed. So we have these ideas for various ways in which it is favorable. For sampling and for just the problem of, say, solving PDEs, where you definitely want to know about all the solutions, I think the fact that we have the predictivity of the energy conservation should be a very helpful thing, right? Just for the usual reason that it is in physics. And here it should be because we can, predict successfully distributing over the different solutions. And so for problems where that's of interest, it seems like it should have an advantage. For sampling, it's very different, and we're just starting to study it. But there's again, let me just say I don't know of any reason why there's not room for improvement on all these fronts. And so although it's very true that there are many algorithms that are working beautifully, presumably there's room for improvement, and these are different enough that hopefully they will find their killer app. But yeah, sorry, that was basically a long-winded way of saying we don't know yet. But thanks for the question.
Well, one idea that struck me during the talk is that because the velocity squared goes as the potential of V, it seems like it would be suited for potentials where the structure of the potential is at the average scale V, so that as you go down, you get structure on smaller energy scales, because that's smaller, because too big a velocity has a dangerous skipping over feature, and now you've naturally scaled the velocity down.
That's a great comment. True. Yeah, and then the question becomes what problems, what data sets or architectures have that feature, right? I mean, but yeah, thanks. That's a great comment.
Can I actually press on a little on this, Eva? So when you do standard Monte Carlo, you get stuck, of course, in a local valley. but with enough noise, you tunnel out eventually, right? And then you go somewhere else. Now here in your model, you slow down because of dBi, as you showed, and eventually you escape again. And can you at least compare these two escape times? You know, is there
Yes,
critical
right.
parameter of noise to which I can compare in the dBi?
Yeah, absolutely. So that's related to the brief comments I made on the Brownian sort of, stochastics, the Brownian motion aspect of, say, SGD, or as you say, Monte Carlo and so on, versus the balancing and the effect of the noise, which is limited by the speed limit in BI. So there are calculations one can do. Again, in shallow regions, BI just by its dynamics just goes faster. So you're right. There are calculations one can do in those contexts. I mean, with sampling, we're very intrigued, and especially because, it remains to be seen how we just started this, but in all these areas, we're working with domain experts who feel there's room for improvement. So in sampling, there's methods where you decide to keep or drop a point based on its comparison to the curve or the function you're trying to sample. Or there's Hamiltonian Monte Carlo where you do use energy conservation, but you sample from the the Gaussian part of the theory, and that gives you your temperature, which behaves in the way you're sort of alluding to. And here it's just very different. It's straight up energy conserving dynamics. Predictions come from the phase space. It does not require a separable Hamiltonian. And there's a big space of these models, right? I mean, sort of like what was called P of X models in the cosmological case. Another thing on our agenda is to try and figure out, which of these types of models should do best. But I'm just saying there's big space to play with. But yeah, I totally agree. The way the others certainly work as well as they do is through the stochastic aspects of it. And but people also discuss a lot how difficult it is to really carefully characterize the noise, even in SGD, because it's pretty complicated noise. The discreteness is essential, and so on. So when it comes to your question about calculability, I think it may be easier for the usual reasons that energy conserving dynamics is easier for that, but we'll see.